Here's an example of a finite geometric sum. Here we're going to use a little trick here and try to factor 2 from these terms of the sum. And the reason we're going to do that is because once we factor 2 out, we will see an expression that is very similar to the original expression. So here we factor 2 out of 2, it becomes 1. You factor 2 out of 2 squared, it becomes 2. This is 2 squared. And we factor 2 out of 2 to the 15th power. This becomes 2 to the 14th power. Now we notice that this is the original sum s without the very last term, the 2 to the 15th power. So it's s minus the very last term of that sum. And this will give us an equation, and we can solve it for the variable s. So this is 2 times s minus 2 to the 15th power. And this becomes 1 plus 2s, 2 times the 2 to the 15th power, that's 2 to the 16th power. Now we move s to one side. 1 minus 2 to the 16th. Factor s, or you can simply combine the two. This is negative s equals to 1 minus 2 16th. S is 2 16th minus 1. Let's apply the same idea to a general finite geometric series. Here we have 1 plus r squared. Again, we factor r from the second term forward. And once we factor r, what we see here inside the parentheses is the original sum s minus the very last term r to the nth power. So we substitute that in here, multiply r out. R times s is rs, r times rn is rn plus 1. At this point, we factor s, and this is s times 1 minus r. We divide by 1 minus r. Now this is true if r is different than 1, because here at this point of the process, we divide by 1 minus r in order to solve for s. So this is true only if r is different than 1. Now what happens if r is 1? If r is 1, you don't even need to do all of that development. This would simply be 1 plus 1 plus 1, because 1 to any power is 1. So you would have 1 added n plus 1 time. S would be that if r is different than 1. If r is 1, then that's simply n plus 1. Now let's study a special type of recurrence relation. It's called a linear difference equation. And here's the format of the recurrence relation. Sn equals to a constant a times Sn minus 1 plus another constant b. Now here the constants are given. However, a here has to be different than 0. Notice that if a is 0, then we don't have this term. This term will be 0, and then all the elements of the sequence of the recurrence relation will simply be b. And also S naught or S0 is given. That means that this sequence here, this formula works for indices n equals to 1 or greater. Here's the first element of the sequence, S naught or S0 is given. There is no formula for that, it's just a given quantity. S1 is defined to be A S naught plus B. S2 is A S1 plus B. But notice that S1, we can substitute that with the previous expression for S1. So we put that in here, and now we multiply A out, and that gives us A squared S naught plus AB plus B. Let's do a few more, and we will see a pattern here. Here is S3, A S2 plus B. Then again, we multiply A times a formula for S2 that comes from the previous element of the sequence. Replace that in here, and we have this expression. And following the pattern, S4 will be A to the fourth S naught. And you can start to see a little pattern here. See, from this term forward, you have A squared A, and this can be written as A naught, A raised to the 0 power. And each term is multiplied by, each power of A is multiplied by B. Here again, you see the same format. So that gives us a pattern in general for Sn. Here we can see the pattern A raised to n minus 1 times B. And the very first term is A to the n times S naught. Because of this pattern from the second term forward, we can apply the geometric series formula, or the geometric finite sum formula. Here we factor B out, and here we have A to the n minus 1, plus A n minus 2, all the way down to 1. And according to the geometric finite sum, this is equal to that. Now, here we have a formula for Sn. Notice that this is a closed formula. It does not depend on the previous element of the sequence. So Sn is defined in terms of n, the index, the initial condition here, the initial value, or the very first element of the sequence, and also in terms of B and in terms of A. You can see that Sn is not defined in terms of Sn minus 1 or Sn minus 2. And this is very useful because let's say, for example, you want to find S50. Normally, you would need the original recurrence relation given by this, right? So S50 would be A times S49 plus B. But in order to find S50, you need S49. In order to find S49, you need S48, and so forth. Now, with this closed formula, we don't need to find the previous terms. We can simply say S50 is A to the 50th power times S naught, which is given, plus B, right, times A to the 50th minus 1 divided by A minus 1. Notice that this formula works only if A is different than 1. What happens if A is equal to 1? If A is equal to 1, then we simply have Sn equals to Sn minus 1 plus B. And what is the difference now? What is the formula for that? S naught plus NB. Let's see why is that. Well, S1 would be AS naught plus B, but we are assuming that A is 1, so this is S naught plus B. Now S2 would be S1 plus B, which is S naught plus B plus B, right? S3 would be S2 plus B. That would be the previous one, S naught plus B plus B plus B. And you can see the pattern here. S3 is S naught plus 3B. S4 would be S naught plus 4B. And Sn would be S naught plus NB. Another observation here is that this formula is actually a result from theorem 9.1 in the textbook. Now, the book uses this formula here that involves a variable c, and where c is defined to be b over a minus 1. Now, where does this come from? So we derived Sn to be that, and the c comes from this simple algebraic derivation here. We obtain, in our derivation, we obtain that part. Well, here we can simply multiply b out, b times an minus b times 1. And then here, we simply factor a to the nth power out of these two terms. And when you do that, you will see the same expression repeated inside the parentheses and outside the parentheses. And the book calls that C. That gives us this a nice formula, an, and then in parentheses S naught plus C, and outside minus C. Either way is correct. It's just a different way of writing the same formula.